Okay. Where did my, sorry. All right, so I want to do, okay, so basically what I'm going to do is I'm going to erase all of this and do a little work on just this, on just the Dirichlet kernel here, to show how we can rewrite the Dirichlet kernel into something nice. Okay, so write down what this is so that you can reference it in your notes as I show you this computation. This is a bad eraser. This one is going to be better. All right. So the function kn of z, which is equal to 1 plus 2 times the sum k equals 1 to n of cosine of kz. Okay, before we add z is equal to x minus y. Okay, so this function here is called the Dirichlet kernel. Okay, now what we're going to do is we're going to use Euler's formula to start rewriting this. So this is equal to 1 plus 2 times the sum k equals 1 to n. So by Euler's formula, this is e to the I kz plus e to the minus I kz divided by 2. Okay, so the first thing that we're going to note is that the 2's cancel, and this is equal to 1 plus the sum k equals 1 to n e to the I kz plus e to the minus I. Whoops. I'm kind of writing this like it's going to be the numerator, but it's just going to be like this. E to the I kz plus e to the minus I kz. Okay. Okay, and so this 1, this is equal to e to the I 0z. Okay, but notice I've got a sum going from 1 to n. I've got positive k's here and negative k's there. So I can just rewrite this in the following way. This is going to be equal to the sum k equals minus n to n e to the I kz. So I'm going to be summing over all of the negative k's and positive k's and get the same thing here. And notice when k is equal to 0, I'm just going to end up with this term here, which is what I started with. Okay, now here, the next step is going to be an exercise. But notice all we have here is a geometric series, or a partial sum for a geometric series. And the main difference from what you probably saw in your Calc 2 class is that we have a sum that's going now below from minus n to n, instead of from 0 to n. But as an exercise, you can show, and should, that this is equal to e to the minus I in x minus e to the I in plus 1x over 1 minus e to the ix. Okay, and so now basically I want to rewrite this as a trigonometric function. And to be able to do that, in the numerator here, I need to not have an n and an n plus 1. They need to be the same argument. Like that, the thing there and the thing there need to be equal to each other. So basically I'm going to take the average, meaning it'll be n plus 1/2 instead of n plus 1. So to do that, I'm gonna write this. So let me just write out what this is, and then we can talk about it. So this is equal to e to the I. This is equal to e to the I times x over 2 divided by e to the I times x over 2. Of course, that's just equal to 1. And then in the numerator, we're going to have e to the minus I n plus 1/2 x minus e to the I n plus 1/2 x. Okay, so if you distribute this back over there, you're going to get that. And if you distribute this over there, you're going to get back to that. And divided by, okay, so similarly, if we if we've divided out by this or factor that out of the denominator will change, and in the denominator we're going to get e to the minus I x over 2 minus e the I x over 2. Okay, now that term's equal to 1. What we have in the numerator is almost sine. It's almost sine of n plus 1 half x, except the sign needs to be flopped and we need to divide by 2i. But same thing here. So if I divide the numerator by 2i, and to balance that, divide the denominator by the 2i, the numerator is minus sine n plus 1 half x, and the denominator is minus sine x over 2. So overall, I'm going to write it and then step out of the way. This is sine of n plus 1 half x over, at some point here, I started writing x's instead of z's. Sorry. Okay, so sine of n plus 1 half z over sine of z over 2. So that is the formula for the Dirichlet kernel. Okay, so that is the formula for the Dirichlet kernel. So I'm going to rewrite the formula up here. So what we have then, there's kind of two useful ways to thinking about this. One, we can think about this as the sum k equals minus n to n, e to the ikz. That's one helpful way to think about it, and this is the other helpful way to think about it. This is sine of n plus 1 half z over sine of z over 2. Okay, so what are some properties that the Dirichlet kernel has? Well, one property is that it's an even function. So why is it an even function? Well, sine is an odd function. I have an odd function divided by an odd function. An odd function divided by an odd function is an even function. One, I know this is an even function, so you might want to take note of that. And two, if I look at the integral from minus pi to pi of kn of z, well, what am I going to get? This is going to be equal to the sum, k equals minus n to n times integral minus pi to pi e to the I k z dz. Okay, so what is the antiderivative of this? Well, I have to split it up into two cases. If k is equal to 0, this is just equal to 1. So if k is equal to 0, this is just equal to 1. And so I'm going to have the integral from minus pi to pi of 1 dz plus everything else, which I can write in this way. The sum k equals 1 to n times integral minus pi to pi e to the I k z plus e to the minus I k z dz, just kind of going back to how we had it before. So this integral here is equal to 2 pi, but notice what's going to go on over here. I'm going to end up, so I'm going to divide, when I take an antiderivative, I'll divide by ik. But what I'm going to get, let me just write out explicitly. This is k equals 1 to n. If I do the antiderivative here, I'm going to have 1 over ik times e to the ikz going from minus pi to pi plus, well, there's a minus sign in the antiderivative, so it'll be minus 1 over ik e to the minus I kz, and this will go from minus pi to pi. Okay, now there are a number of ways to see this, but what we're going to end up with is both of these terms is going to be equal to 0. Okay, so why is that? So if you just think about e to the I kz, this is 2 pi periodic. But notice if I plug in pi, so if I just look at this term right here, I'm going to get 1 over ik times e to the ik pi minus e to the minus I k pi. And if I divide here by 2I, and then therefore I need to multiply here by 2I, this is now just sine of pi, which is equal to 0. And something similar will be true over here. This will be equal to minus sine of pi or something like that, which is also equal to 0. Or sine of k pi and minus sine of k pi. Either way, they're equal to 0. So, in other words, this is just equal to 2 pi. Or, if I divide everything by 2 pi, the integral of 1 over 2 pi times integral from minus pi to pi, kn of z dz is equal to 1. Okay, and this will be extraordinarily helpful to us in just a moment. Okay, so now let me sort of, using the Dirichlet kernel, let me rewrite what it is that we have, or what it is we're trying to show here. So again, our goal is to show that the impartial sum converges to f of x, but this is the same as saying their difference goes to 0. So what we want to do is we want to show that Sn of x minus f of x, we want to show that goes to 0. Okay, so Sn of x, we already saw this is equal to 1 over 2 pi times integral from minus pi to pi f of y, kn of x minus y dy, and then minus f of x. Okay, but now here is where we're going to use the fact that the integral of kn divided by 2 pi is equal to 1. Actually, first we're going to do a change of variables. First we're going to do a change of variables. We're going to say let's say z is equal to minus, okay, so y minus we'll see in just a minute. So z is equal to minus x minus y. And so the integral variable is dy, so this tells me dz is just going to be equal to dy. Okay, and so now what we're going to get, we're going to have 1 over 2 pi. I'll talk about the limits on the integral in just a second. So if z is equal to minus x minus y, this is the same as saying z is equal to y plus x, or sorry, y minus x. And so y is equal to z plus x. So this is f of z plus x, not k. Okay, now here, I should be putting kn of minus z dz. Okay, but kn is an even function. So kn of minus z is just equal to kn of z. And so this is what we have. Okay, now the limits of integration, if z is equal to y minus x, okay, then my limits of integration here should be y plus pi, that's y minus pi, and my limits of integration here should be something like y minus 2 pi. sorry, I got that backwards. This should be minus pi minus x, and this should be pi minus x. Okay, but remember, we're assuming that our function f is periodic, and this is periodic, and the length of this interval is 2 pi. And so, using the periodicity, this is just equal to minus pi to pi. Okay, if you have a function that is periodic that is 2 pi periodic, it could be even more periodic. But if a function satisfies g of x plus 2 pi equals g of x for all values of x, then the integral over any interval, so if I go from a to a plus 2 pi, this is going to be equal to the integral from over any interval of length 2 pi. So b to b plus 2 pi. I mean, that's what it means. That's one of the things it means to be periodic. Okay, so this is what we have, and minus f of x. Okay, now here's where we're going to use the fact that that the integral of kn is equal to 1, because what's really true is I have my f of x, but this is equal, if I have my kn of z and integrate from minus pi to pi, well, as far as z is concerned, f of x is a constant, and the integral of kn over 2 pi from minus pi to pi is equal to 1. So this is just equal to f of x. And so I can write this as the integral of 1 over 2 pi times the integral from minus pi to pi kn of z times f of x plus z minus f of x dz. Okay, and now here is where we're going to use the differentiability property of f. I've got f of x plus z minus f of x. Okay, this is like if I think about the mean value theorem, I know this is going to be equal to f prime of z, or f prime of some number in between x and x plus z times z. Okay, but if I continue, I'm going to rewrite actually what kn of z is. And so this is 1 over 2 pi times integral minus pi to pi. Okay, so I'm going to have sine of n plus 1/2 times f of x plus z minus f of x, and then divided by, I'm going to now divide by the numerator in the or the denominator in the kn, which is sine, sorry, there's a z here, sine of z over 2 dz. All right, now I will let you prove this for yourself, but these functions, sine of n plus 1/2 z, these are orthogonal relative to this inner product. Okay, these are our orthogonal functions. If you do the integral, if you pick two different values of n and do the integral of those products, you get 0. So these are a sequence of orthogonal functions. Okay, so what we're saying then is, if I define this function here, dg of z, okay, this is like, I'm doing the inner product of an orthogonal, I've got a sequence of orthogonal functions times g of z here. So let's just call this phi sub n. Okay, and so what Bessel's inequality implies then is the following. So what Bessel's inequality implies is the following. The sum n equals 1 to infinity of g with these sine functions So this is in plus 1/2 z. This squared is less than or equal to the integral. This is less than or equal to the integral. There's going to be a constant here. So let me say it this way. Is less than or equal to the integral from minus pi to pi of g of z squared dz. Okay, so in other words, by the test for divergence, these go to 0, as n goes to infinity. Each one of these goes to 0. Okay, so how is that going to help us? If I can show this integral is finite, what it means is that each one of these guys is going to 0 as n goes to infinity. But that's exactly the same as showing that integral. I mean, this is that integral. So it's the same as showing this integral goes to 0 as n goes to infinity. In other words, Sn of x minus f of x goes to 0 as n goes to infinity, which is exactly what we want to show. Okay, and so in the next video, I'm just going to show that this integral, if g is defined in this way, that integral is finite.